And I'll pull up the images right here. Okay, what questions we got? And for some reason, I'm not seeing the chat. Hold on. Stop sharing for a sec. Okay, for 5, 7, 9. Okay. And also 14 and 15. Okay. And 23, 25, 33, 35. Okay. So let me just, let me kind of just go in order right now. I think that's kind of fair. I'll go in order for the first half of it. So, excuse me. All right. Oh, can't minimize my recording. Okay, no worries. Share screen again. Okay, we're still recording. All right, let's start with 1 through 9. What you really want to do here for these problems, I strongly suggest you go about these graphically. That's what I do first. Look at these graphically. And from the graph, then tell me where there's a point discontinuity and what type it is. So for graph number 1, and I'll explicitly tell you to do that, that's what I want. It's too hard to do these analytically. So again, if I ask a question like this, I will explicitly say this graphically. There is a vertical asymptote at -2 for number 1. And I think it looks like this because you're squaring. So it's pretty clear you have a vertical asymptote. That's an infinite discontinuity. And it happens at -2. More formally, why is it infinite discontinuity? That's because your LHL equals positive infinity and your RHL. Of course, f -2 does not exist. That's the first condition of continuity. The limit as x approaches -2 of fx does not exist. That's the second condition of continuity. And forget about the third condition. The first two don't work. Then, of course, the third one's not going to work. The third one is if f of -2 equals the limit. But they don't exist, so don't worry about it. But more formally, it's because your left and right hand limits are both going towards infinity. That's why it's an infinite discontinuity. And the graph shows that. Or numerically, you can plug in numbers close to -2, and that will happen. So that's number 1. For number 3, if you graph number 3, it's a nice smooth curve. It has a little like bump, like that. No breaks in it. It's all good. No discontinuities. Everything's fine. Number 5. Number 5 starts at -3/2 and looks like this. Now, this is kind of weird. Where is this not continuous? Well, it's not continuous where it's not defined. So, not continuous at undefined x values. Because in order to be continuous, don't you have to have f of whatever to exist, right? So for example, would number 5 be continuous at x equals -2? No, of course not. It's not continuous at x equals -2 because it's not defined at x equals -2. F of -2 does not exist. So that's what's meant by all points on the domain is where it's not continuous. That's all. It's not a specific type, though. You can't really label it. So you don't worry about labeling it. For 7, we did that in example 2.1 notes. Let me clear my screen. For number 7, graphically look like this. So again, graph in Desmos or in your graphing calculator, it'll look like that. It's not defined. F of 0 does not exist. And the limit as x approaches 0 of f of x does not exist. Typically when that happens, that'll be a jump. Now that could also happen for an infinite discontinuity, but an infinite discontinuity, your left hand, right hand limits were positive or negative infinity. Here, my left hand limit is going to be -1. My right hand limit is going to be +1. Those don't equal each other. Hence, limit does not exist. But because those are finite values, we would call that a jump discontinuity. If they're negative and positive infinity for left right hand limits, then I make an infinite discontinuity like I did for number 1. Finally, for number 9, number 9 is kind of weird. It looks kind of like this, I think. No. I think there'll be a hole here, I think. Yeah, if you plug in like negative, like excuse me, if you put like negative 0.0001, then you're doing that, which is essentially close to 0. But I believe there's a hole here, but also there's a vertical asymptote over here. We still call it infinite discontinuity because of the infinite nature on the right side of the y-axis. Again, approach these graphically. And if you get close to 0, I don't know why it says 0, 0. There shouldn't be a point at 0, 0. I don't know why it says that. Maybe a hole there. You see, this goes up forever. So that's that one. One sec here. Okay. So hopefully you guys are cool with that. 11 and 12, I think, should be pretty straightforward. Don't think there should be any problems there. I don't think anyone had any questions about that. Just yes, no questions. All yes for 11. And again, use appropriate one-side limit if it's an endpoint. Of course, for 12, it's yes, yes, but no for the last part because the point floats off, so it's not continuous. 13, is it defined at x equals 2? Well, no, because I don't see anything there, so no. So is it continuous? No, because it's not defined. 14, where is it continuous? Everywhere in this interval, from -1 to 3, except for x equals 0, 1, and 2. So 0, 1, and 2 are not, either they're not defined at x equals 0 and 2, or at 1, the limit does not equal f of 1. So those are discontinuities there. And by the way, those are all considered, that's a jump discontinuity at x equals 0. Those are removable at 1 and 2, and even at 3. What value should be assigned to f of 2 to make it continuous? Well, obviously you want to plug in the hole. So just say f of 2 is 0 to make it continuous. What new value should be assigned to f of 1? Well, again, you want to plug in the hole, make it 2. So f of 2 should be 0 to make it continuous there. F of 1 should be 2 to make it continuous there. Is it possible to extend f to be continuous at x equals 0? No, because unfortunately, the left right hand limits do not equal each other. If they do, the limit does exist, and you can make it continuous. Just make sure this point fills in the gap. But unfortunately, can't for 17. But for 18, you can just put a y value of 0 at x equals 3, and you're good. You could extend the function, make it continuous there. So hopefully that tackles questions for that part of the homework. Let me see if I took care of that. And someone also asked why the answer to 7 is both infinity and negative infinity. Let me look at that one more time. No, 7, the answer is just x equals 0. Oh, or maybe, oh, are you telling me page 97? Got it. I'll get there in a little bit. Don't worry about that. Sorry, I was confused with number 7 was being asked about that. Okay, we'll hit up 25 now and 33. And someone asked, can you quickly go over how to find limits when x is approaching negative positive infinity? Yes, I will do that. I'll cover that on page 97 of the homework. Okay, so let's hit up 23, 25, 33, 35. Let's do that next, because there are a few people asking about that. By the way, these here, I don't think anyone asked about these, so maybe you guys are cool. Oh, come on. Hold on. There we go. Yeah, these here I think are pretty straightforward. Find each point discontinuity. So usually what you do is just wherever you see the boundary for the piecewise, just plug in 2. And you'll see that they equal different y values. So obviously it's x equals 2, but it's not removable. Removable is when a point's floating off. This is a jump discontinuity. When the one-side limits are different, so removable means the limit exists. To be removable, you need the limit to exist. Now here, f of 2 is defined, but the left-right-hand limits, and the limit exists also, but the limit does not equal f of 2. So that's why it's removable. 21, that's an infinite discontinuity because of the vertical asymptote here on the left side. For 22, it is removable. F of negative 1 is 2, but the left and right-hand limits here is going to be 0. In order to make it continuous, you'd have to make that a 0 over here instead. For 23, obviously it's not continuous at 0 and 1. Definitely removable here, but it's a jump at 1. 24 removable at 2, but a jump at 1 again. So, all right, 25 and 27. You want to extend the function and make it continuous. So here's what I would do. I would simplify this by doing that. What crosses off here? X plus 3. So you can write it 2 ways. You can write it like this. Or you can write it like this. Either one's fine. You can write it like that, or like that. So what you do is you can write as a piecewise function where one expression is like the original, but state what x value you can't plug in. We can't plug in, I meant to say negative 3, by the way. My bad. And actually, I meant to say this is negative 6. My bad also. Sorry, I messed that one up. Sorry. So write the function as is, and state what x value you cannot plug in, which is negative 3, not 3. My apologies. And then state what the y value would have been if you were to plug in negative 3 in the simplified form. Simplified form is x minus 3. If you plug in negative 3, you get negative 6. Or just write the simplified form, and that would be fine too. Because what's going to happen if you graph x minus 3, it looks like this. At x equals negative 3, it's going to be filled in right here. Now, technically, this is what should be happening. But because you want to make it continuous at that point, that's why we either write as a piecewise to fill in the hole, or just write x minus 3, because that is what it is. It is x minus 3. So we could do it one of two ways. And just so you know, if you want to reference this in the notes, I believe if you go to the 2.3 notes, fill that notes. I'm just being mindful of time too. So I want to make sure you have enough time to do some group work. But we go to 11:40, so we're still okay. Example 8. And I probably suggest you guys maybe do an audit of your notes. Make sure your notes are accurate. So all the filled out notes are in Schoology, just so you know. That might be a good idea to do this weekend. Okay. And 27 works the same way. You just have to look graphically what's happening. We know that we know the limits is 1 when x approaches 0. So this is fine. And actually, I don't think you can write any other. I think you have to write this as a piecewise. I don't think you have a choice but to do that. Whereas here, this row is y equals x minus 3, but you could write it as a piecewise like I did just earlier. Okay, we're okay there? All right. Okay. Let's keep moving. 33, 35. Hold on. What the heck am I doing here? Hold on. Okay. Homework images. There we go. Okay. These problems here. I probably won't ask this on our test because it's a little too open-ended, but we did have this as one of the in the lecture notes. Right here, example 9, and I did reference that. So remember, in Schoology, I did provide hints to kind of help you out. So yeah, I said theorem 7 refers to near the bottom of page 4 of the 2.3 notes, reference example 9. Again, it's open-ended. So you could said like, I don't know, hold on, it's being a little annoying. There we go. fx equals x, g of x equals x plus 1. Are both those continuous functions? Yes, they're both linear. And then you can say h of x is root x. Root x is also linear, sorry, is also continuous on its domain. So you can now write a composite, h of f of g of x. And that's okay. You're good there. No problems. So that shouldn't be a problem. Or you could have done this. Forget about g of x. Say f of x that. That's also continuous too. All rational functions are continuous on their domains. And you could rose h of f of x. That would find all. So it's kind of open-ended. For 35, you could have said, you know, f of x is 1 minus x. That's continuous. It's linear. G of x is q root of x. That's continuous. Cube root. Why not? And then you say h of x is cosine x. That's continuous too. We've seen cosine x. There's no breaks in it. So h of g of f of x will, of course, be continuous, according to this theorem here, or what we discussed in class. So that's that. Okay. Let me talk about the limits really quick before I do IVT. Someone asked about number 7. And I think, did anyone ask about anything else from this page here? Hold on, let me look at the chat. Yeah, someone asked about number 7. Problems 5 and 7, got it. Okay, let's do 5 and 7 here. Okay, number 5, I like this one a lot. This will be on our test for sure. I could put it either multiple choice or free response, but I still need to see your work. You have to do this. You got to find the LCD. See, if you were to plug in 0 right now, you have a problem. 0, 0 is no good, right? So we got to get a little creative here. Our LCD is going to be 2 times the 2 plus x. So what this means is we got to change up these fractions here of the red. 2 plus x for this guy, x for this guy. Okay. So if I clean this up, you'll have x minus parentheses 2 plus x all over 2 times 2 plus x, and the whole thing over x, or over x over 1. Now, if we work all this out, that's x minus 2 minus x times 1 over x. Don't get lazy, got to write the limit notation just so you know. The x's cancel. Well, actually, yes, the x's cancel. Wait, no. Let's make a mistake somewhere.
I think the left side should be multiplied by 2, not by x.
Yeah, I'm sorry, guys. See, I'm human. See, I caught myself. So this is what happens in real life. You catch yourself and you make these mistakes. Okay. So let me erase that here. Okay, so, because I knew something seemed weird, right? So it wasn't quite working the way I had hoped. That's what I should have done. Okay, now it's better. And flip that over. The 2's cancel. So you have negative x, and the x is canceled as well. So you have negative 1 over 2 times 2 plus x. Now plug in 0 for x, you get negative 1/4. Now on the test, what this for fill in the blank, you put positive 1/4 because maybe you didn't distribute the minus that x here. Don't worry, I'll see you work. I'll see you make that careless error. If it's a 4-point problem, I'll give you 3.5 out of 4. That's why you must submit your work though, so I can help you out. Otherwise, I don't know how to help you. Let's say you did have as negative 1/4 and you just accidentally punched it in wrong. Then I'll see your work again. So again, make sure you submit your work. This is going to be a great way to back up your, all the great work you'll do. For 7, here's the deal. This is higher than this, so we don't expect there to be a horizontal asymptote when x is approaching positive negative infinity. Now, analytically, what we do is this. You multiply top and bottom by the highest degree of the denominator, which is x cubed. If you do that, you get x4 over x3 plus x3 over x3 12. And again, this is the limit as x approaches positive or negative infinity. Clean it up. You have x plus 1 over 12 plus all this junk here. Now, again, the limit as x approaches positive or negative infinity. We've talked about this many times. When you have something like of this form, 1 over x to the n, that limit is just 0 if x approaching positive or negative infinity, assuming that n is positive. So that just goes away. Sometimes draws this arrow with equals 0 on the upper right corner. So that just goes away. So what are you stuck with? X plus 1 and 12. That's a linear function. So what happens when x approaches positive infinity? What do we expect this expression to head towards? Positive infinity. What if it's going towards negative infinity? So if I take the same expression here, that's x, that's a positive slope, but you're going to the left, negative infinity. That's why you have two different answers here. So the first one is for when x approaching positive infinity. The second one is for when x approaching negative infinity. That's what happens. And that's the analytical work you would show to back it up. So hopefully that makes sense.
Wait, so for number 7, when the degree on the denominator is lower than the degree on the numerator, it doesn't mean that there's no limit. It just means it's infinite.
Sorry, we said when the degree of the numerator is higher than the denominator?
No, lower.
Oh, when the denominator is lower, it's y equals 0.
But then if y equals 0, then why isn't number 7 0?
Because the numerator is higher degree. You just said the other way around.
No, okay. I mean, if the numerator is the higher degree.
Okay, gotcha now. Okay, all right.
Then if the numerator is the higher degree,
okay,
then
good.
It doesn't mean that there's no limit. It just means that the limit is infinite.
Yeah, exactly. Yes, 100% correct. Yes.
Okay.
Technically, you could say it does not exist. Because what is infinity, right? We don't know what that really is. It's some abstract. But being a little more explicit, yeah, it's good to say positive and infinity. Yes. But if you said D and E, you've been fine too. Yeah, and that's totally legit. But if the degree of the denominator is higher, it is 0. And I thought that's what you said, so my apologies. Okay, let's quickly do an IVT. Actually, I'm looking at the time. I want to make sure you guys have enough time to do some work. Let's do this. There's going to be an IVT in the board problems. It's going to be the second problem. I'll make sure I'll address that when you guys get back from the breakout rooms. But really quickly, when you're doing IVT, reference example 11. You'll need an equation. You'll need to move everything to one side. And then you have to come up with some x values that make the expression positive and some that make it negative. And then you're going to use the IVT statement to answer the question. So example 2 is a great way for you guys to practice that. But I really want to make sure you guys have time to practice. So I'm going to stop the recording right now. I did actually record IVT number 45 in period A. If you do want to watch that, that is there, and I'll post that for everybody. But